Northern Kenya. Night air still, lake surface glass black. A seismic array west of South Island volcano registers a tremor too small for human notice, yet precise enough to mark a change deep below the Turkana Basin. For decades, geologists believed this section of the East African rift crept forward at a slow, predictable pace. But recent fault logs show the movement has accelerated. A team analyzing 10 years of high-resolution lakebed sonar and seismic data has uncovered a measurable surge in slip rates, an increase of nearly 0.2 of a millimeter per year across 27 mapped faults. At first glance, it's minor. Over centuries, it's transformative. The crust beneath Lake Turkana, one of the oldest active rifts on Earth, is stretching faster than at any time since humans began recording it. The pattern began roughly 5,000 years ago. Something shifted after the Great Lakes of East Africa dropped by more than 100 meters. Less water meant less weight pressing down on the rift floor. The crust flexed upward, stress fields realigned, and molten rock in the upper mantle began to rise. Pressure built beneath a small volcanic center called South Island. Calculations from new models show Coulomb stress changes exceeding 600 kilopascals, enough to unlock faults that had been sealed for millennia. Scientists traced this chain reaction using a numerical simulator called PyLith. They modeled the basin with a virtual lake that drained and refilled through time. When the lake shallowed, the simulated crust bent like a released spring. The response was immediate. Fault lines opened, magma intruded, and extension rates climbed. A drop of 100 meters in surface water produced subsurface stress swings equal to those seen during major deglaciations elsewhere on the planet. The discovery reframes what drives continental breakup. Tectonic forces remain the engine, but surface water acts as the throttle. When the load lifts, the deep system breathes. In Turkana's case, it exhaled. The area today looks tranquil. Sand plains, a shallow green lake, no visible fractures from the shore. Yet beneath it, the South Turkana Basin is a lattice of active faults aligned north-south in a 30-kilometer-wide zone. GPS stations positioned along this corridor record extension of up to 5 millimeters per year. Most of that movement concentrates near the volcanic axis, where a mid-crustal magma chamber about 3 kilometers in radius lies 10 kilometers below the lake. Samples of trapped fluids from ancient eruptions confirm repeated magma recharge episodes during the past 5 millennia, the same interval when the basin began to accelerate. Finite element modeling shows that the magmatic pressure alone could explain the increased fault motion. When melt influx rises by just 1/10 of a cubic kilometer per 1,000 years, stress on nearby faults spikes beyond the threshold for slip. Combined with reduced surface loading, the effect compounds. Fault planes slip, rift segments subside, and the lakebed tilts eastward. This is more than a local phenomenon. The same mechanical feedback can occur anywhere large lakes or ice sheets lose mass above active rifts. In Iceland, similar unloading after glacial retreat has boosted magma output. In the American Basin and Range, Paleolake drawdowns correspond to heightened faulting episodes. What makes Turkana distinct is the precision of the record, the first direct seismic evidence that this feedback continues in real time. The implications are geological, not apocalyptic. The African continent is already splitting along 2 main arms, one running through Ethiopia, Kenya, and Tanzania, the other along the western Great Rift. The Turkana Depression links them. Acceleration here could determine how quickly that linkage evolves into a true spreading center, a nascent ocean trench forming in slow motion. Satellite interferometry now monitors the region monthly. So far, no major earthquakes have followed the increased slip. But stress transfer models suggest that as magma pressure fluctuates, shallow rupture events could become more common. In 2022, a swarm of microquakes beneath the lake matched the stress signature predicted by the unloading simulations. None reached the surface, but each traced the outline of the active magma system like a heartbeat monitor. The evidence is plain. The rift responds to surface weight. When it lightens, the crust stretches faster, magma ascends, and the process of continental division speeds up. This isn't theory, it's measurement. In the field, researchers still read the sensors by hand each dawn. The data stream hums quietly through a relay station near Lodwar, bound for servers in Syracuse and Auckland. Every few weeks, another line on the fault model sharpens. The numbers keep rising. 5,000 years ago, a lake receded and the land beneath began to tear. That tear has not stopped. It is widening now.